All right, guys, welcome back. We've been discussing over the last few lectures some of the properties of basic or simple chemical kinetics. And we've spent a bunch of time thinking about how the sort of features or the um, description of a given process, right? For example, when we've been using a lot, a process like this, unimolecular conversion of A into B, how that process is described by a rate equation that can be solved and then find a rate law that describes with precision the temporal conversion of A into B, right? We've talked about reversibility. We looked at the consequences of that. More importantly, what we saw in the last lecture is that while these rate laws can vary with very high precision, explain the temporal, can describe the temporal progression of a process like this, these rate constants, which is where the sort of kinetic behavior at some level, what governs the kinetic behavior, the magnitude of those rate constants, they really only acquire physical meaning when they're connected to an energetic explanation for their values, right? And we saw that specifically that comes from transition state theory, right? Where we talked last time about this idea that the reason a given rate constant has the magnitude it does is because the size of that rate constant is related, right? I'm just going to draw this diagram out again. That reaction coordinate and energy here again is that sort of free energy of the reactant. And we have over here the free energy of the product. And we saw how the reaction coordinate is described by this free energy diagram, where the conversion of A into B goes through this high energy, transiently, very, very transiently populated state that's in transition between A and B, called the transition state, that gets this double dagger symbol, right? Right. And we saw how it's the size of the energy barrier here between the transition state, right, and the A, right? So between the reactant here, that then governs the magnitude of that forward rate constant, because the size of that delta G naught double dagger is directly related or defines the magnitude of that rate constant in transition state theory. And likewise, the reverse reaction here, right? That magnitude of that rate constant, the reverse rate constant, is then directly related to that free energy difference between the product, right, and the transition state. Okay. All right. We also saw then that a really key idea, one of the great things that transition state theory provides for us, is a way to explain catalysis. Specifically, transition state theory provides this simple idea that all a catalyst has to do to make a reaction go faster is lower that transition state barrier, right? So that if this barrier here, the sort of delta G1, the forward, say, reaction catalyzed, right? If that's a lot smaller than the delta G1 uncatalyzed, right, the reaction is going to go significantly faster, right? Because the rate constant is going to get bigger, right? And things are going to happen better, right? Okay. So the whole reason for setting all this up, right, is because of the importance in biochemistry of catalysis, and specifically catalysis through enzymes, right? That's where really the big picture of where we're heading next. And doing this, right, is the big deal that enzymes are doing. What they provide is that reduction in the transition state free energy barrier that, again, remember, doesn't just make the forward reaction go faster, also makes the reverse reaction go faster. But if this barrier here is a lot smaller than this barrier here, and this free energy difference between the ground, the reactant, and the product state is balanced this way, you're going to get the equilibrium faster. And with that free energy difference between B and A, you're going to make B, right? Okay, but remember, catalysts do not bias the reaction in one direction or the other. They lower that transition state barrier, which means you get to equilibrium faster. That's what enzymes do for all these incredibly important biological reactions. So just as a sort of general introduction to this idea, it's probably worth thinking about a little bit how enzymes would do that in just the biggest possible picture sense, right? How would an enzyme lower that transition state barrier? And if you think about what we've just studied before we got to this topic, right? That we think about hemoglobin binding oxygen, right? Or you remember some things from your undergraduate biochemistry, you'll know some of the reasons why enzymes are able to do this so well, because they're using the same idea here, this sort of highly specific, right, binding, right? But where enzymes are recognizing features of the transition state, which is sometimes abbreviated TS, sometimes a TS double dagger, or just TS, right? So that is just such a really key idea, and in a big picture sense of what enzymes are doing, that it's worth thinking about this in sort of general terms, right? Energetically. So if you recall, right, if we know we've got a free energy difference here, right? Say for this transition between the ground state and the transition state, right? Let's say delta G double dagger 1. Well, we could use the Gibbs equation to write that out and sort of think about this in sort of a big picture way. Delta G naught double dagger, we can decompose that using the Gibbs work function into the enthalpy contribution, right? Plus, minus T delta S, the entropy contribution, right? So what we're thinking about here, we have this free energy difference, right? Getting between the ground state and the transition state. If we can't get the transition state, we can't make product. We can decompose that free energy difference into the enthalpy and entropy components. We can ask, sort of in the same way the Gibbs work function lets us ask things about, other reactions like we talked about. Why is the transition state so high in energy? Why is it so positive? Why is it so hard to get up there, right? So when you think about that, why would the enthalpy, right? If this is going to be positive, if delta G not double dagger is going to be positive, what are the things that would make it big and positive? Well, one thing is if the enthalpy, right, the dagger is, significantly greater than 0, that's going to make the Gibbs free energy greater than 0. So why would that be? What are the things that would make the enthalpy of getting to the transition state large and positive? When you think about that a little bit, what you know about how these chemical reactions have to work. Any ideas? All right. Well, one possibility is in many cases to break a chemical bond, for example, or sometimes even to make them, you have to impose strain, right? You have to start moving atoms away from each other in order to try and break that bond. That's going to be enthalpically very unfavorable to do, or basically have to put energy into that system to basically rip those two atoms apart from each other and move the electrons around. That's enthalpically unfavorable, right? Okay. Another possibility is that the transition state maybe requires an unfavorable charge distribution, right? For example, there's only one way to get to a product from a starting point. And to get there requires some high density collection of charge of exactly the same kind. We're going to see an example of that when we talk about hydrolysis of ATP. That's enthalpically extremely unfavorable, right? Cramming a bunch of charge together in a small volume, it's a hard thing to do, right? So that's going to make getting through that essential transition state difficult, right? Okay, and there are other examples along a similar line. How about on the enthalpy side of things? Sorry, the entropy side of things. Well, to make delta G larger and positive, that means we're talking about a decrease in entropy, right? The entropy change to get to the transition state is going to be potentially very large or large and negative, so that T delta S becomes positive, making delta G not double dagger large and positive, the transition state very large and positive. Okay, well, what could cause that? You just think about getting a reaction to go. Well, one possibility is that the transition state could require some improbable, right, orientation, right, where you've basically got to get some set of atoms and their orbitals positioned in just the right way for the chemistry to happen. But to do that, you've got to get rid of all kinds of rotational, translational, potentially other degrees of freedom, and keep the molecule that way for some period of time. That's entropically unfavorable, right? There's going to be a cost associated with that. You got to make the entropy of the system lower, which is energetically unfavorable. That's going to make getting there, a transition state, harder to do, right? There's another part, just simple molecularity. Right? If you think about sort of bimolecular reactions, A plus B, right? You got two different molecules that are just hanging out doing their, high entropy thing. You want to get them to react, you've got to get those guys potentially together for some period of time, not just zipping around all over the place. And they got to stay there long enough for the orbital exchange or electron exchange and bonding orbitals to form. That just intrinsically is going to be entropically unfavorable, right? So there are other additional explanations that fall into a similar category, right? So enzymes basically are going to use binding energy to solve this problem, to compensate for those unfavorable enthalpy and unfavorable entropy terms that are inherent to a given chemical transition, right? Okay, now there are so you can sort of categorize how enzymes do this into roughly sort of 6 general categories. It's a lot more detailed than that, but there's 6 sort of big picture categories that we're going to sort of walk through in terms of how enzymes do this. And we're going to get a start of that in the next lecture, or excuse me, the next video.